It's good to know. I'm glad to, I'm sure other people are picking up on the stream.
Yeah, it's just now started streaming, so but
Well, good,
I'll have to
good.
fix it to back where it was. It's just it went down on me. It's
That's
like
okay. You know
all
what?
all of my
It's live.
graphics and everything are now just gone.
It's live programming.
Yep.
And I can share my screen for any graphics and stuff today, so you don't have to worry.
The fact that I got it up and running in less than 10 minutes is quite impressive. To be honest with you.
Kudos to you, sir.
Lucky, because
Yeah, kudos to you.
I don't have your book anymore. Where's your book now? Ugh, got that, but I need the book. Layers. 2 minutes.
And we're going live on time, so good for you.
Right. Logos are loaded, but your book's not. Good
There
for
we
you.
go.
Might as well just take it live. So, in three, two, one, I'm putting you on camera.
Hey, welcome everybody. Dr. Daniel Barth here with this week's episode of How Do You Know?
Do you want
This is
to?
episode
Do you want to run your
63.
counterpart? I got the video for your counterpart, the
Oh,
acting
okay.
professor.
Yeah, go right ahead.
We don't have to if you don't want to. I don't care.
Oh, yeah, we can just jump into it.
All right.
We can jump into it. And
It's a
happy to be here once again, sponsored by Explore Alliance, and kudos to them. And of course, also sponsored by the book Star Mentor. Hope you all. I'm starting to see more reviews on Amazon and other sites, so thank you all very much. Also, for anyone who is in the Northwest Arkansas area, I will be appearing this coming weekend at the Arkansas Dark Sky Festival, sponsored by the Arkansas Natural Sky Association. And that's out at the Buffalo River State Park, the Tyler Campground. And this is a nationally designated dark sky park. So, this is a really lovely place to be doing astronomy. I'm going to be giving constellation tours. I'll also be talking about astronomy with binoculars, and I'll have my giant 127 millimeter aperture binoculars out there for the sky show through the evening, both Friday and Saturday. So if you're in the area, I hope you'll take a chance and come out. We're expecting a good crowd. We've got a lot of people pre-registered. Anyway, this week, as promised, we're going to talk about the DART test. This is that NASA asteroid colliding spacecraft that's been in the news. And I've been getting questions about it. And so I thought it would be a great chance to talk about this, especially since a lot of the news has been talking about what DART does, but not what DART is for. And that's an interesting distinction. So, DART, D A R T, is the Double Asteroid Redirection Test. And the whole idea of this mission, and this has gotten out there pretty well in the media, is that NASA decided to crash a spacecraft into an asteroid and see if they could change its orbit. And this is a really important thing. But I wanted to back everybody up a bit because this is not the first time we humans have done something like this. The idea of whacking an asteroid, as Joe Pesci might say, the Goodfellas. Well, guess what? This isn't the first time. The Hayabusa 2 mission from JAXA, which is the Japanese space agency. Hayabusa, by the way, means peregrine falcon, which is just a really cool thing there. So This was a sample return mission. And the sample return mission was launched in 2014. When we do these things, folks, these missions to asteroids are not like, Apollo. We're going to go up, we're going to go to the moon, we'll be back in a week. You don't have to forward my mail. It's not like the space station. Oh, we're going to go up, we're going to be up there a couple months, 6 months, we're going to come back. No, these asteroid missions are multi-year excursions. Hayabusa 2 launched in 2014, and it rendezvoused with the asteroid Ryugu. And I'm sure I'm massacring that name. Ryugu was rendezvoused with in June of 2019, and Ryugu is a primitive carbonaceous asteroid. We have carbonaceous, rocky, and metallic asteroids. The carbonaceous type are the most common. And the carbonaceous asteroids are thought to contain primitive materials from the origin of the solar system. So we're literally looking at objects which are unchanged for 4.5 to 5 billion years, which is really exciting because how do you rewind the clock? Any materials we have access to on Earth or from the moon or from Mars have been subject to geological processes, atmosphere, solar radiation, heating, water, erosion, chemical reactions, compression by gravity. And so these materials are anything but pristine. Rocks on the surface of the Earth, you'd be hard-pressed to find a rock on the surface of the Earth that's more than 1 billion years old. Stuff from the lunar surface, yeah, you can get stuff that's 3 to 3.5 billion years old. Mars tends to be a very ancient planet. But as I say, there have been a lot of processes happening on the surface of these planets. You go out to an asteroid now. Those things, there's no appreciable heat. Solar radiation is the surface, couple of centimeters only. There's not a lot of impacts because these things don't have big gravity wells. So large objects don't tend to fall in and strike them. And so you get these very pristine things, which is very exciting. Hayabusa was a very complex mission. It contained 4 rovers, actually hoppers. Now, many of us have seen the videos from Boston Dynamics and other companies where they have robot dogs with legs and they hop and bounce. These weren't like that. The gravity on the Ryugu asteroid is so low that what they had, it's much more like the vibration alert on your phone. They had flywheels with weights that were off center. And so when this thing would go brr, it would vibrate. And in the low gravity, it would literally hop off the surface of the asteroid, travel several meters before settling down again. You can't use standard propulsion. It would be virtually impossible to walk across the surface of one of these objects. You could have a backpack. You could fly around it. You would literally have to fly into it. If you wanted to land on it, you would probably need some sort of, you would either have to really take your time falling. Falling from 20 meters might take a couple of hours, very low gravity. And once you touch, if you're not very careful, you're going to bounce. These hoppers, some were more successful than others, but these objects would land and take some pictures, and then the little off-center vibratory propulsion would buzz, and the hopper would go a few meters and take more pictures. The spacecraft also contained a couple of what we would probably now call CubeSats, small microsatellites which were launched to be outboard and take pictures from farther away. But one of the interesting things they did that applies to DART is Hayabusa 2 shot the asteroid Ryugu. So they had the first incident, the first shooting occurred when Hayabusa 2 drifted down, and it looks like a mosquito, folks. It's this cubical satellite about the size of a dishwasher, and it has large solar power wings that extend out a couple of meters on each side. Then it has this proboscis that hangs down. This thing comes down so the proboscis touches first. That's the sample collector. And the first time they wanted to gather some surface materials. So when the when the spacecraft proboscis was just a short way above the surface, they fired a 5-gram tantalum bullet. Now, people have said, why did they use tantalum? Well, it's a fairly exotic metal. Not only that, it has a really interesting and distinct spectrographic signature. So when they get this stuff back, these samples won't be back here until about 2024. When they get the samples back, then if there's any tantalum in them, we'll know, aha, that came from our bullet. That's not natural to the satellite. But they fired this 5-gram, and that's about the weight of a nickel, or it's a small coin. And they fired this in, bang, and it hits the surface and it blasts the material up. And then the proboscis has kind of a basket to capture material. And it was collected in what they call the sampling horn. Well, they knew that the surface material from Ryugu would have been changed over billions of years. Solar radiation, and we're talking the whole full spectrum from infrared to gamma from our sun. There's no atmosphere to filter out harsh radiation as the Earth's atmosphere does to us. And solar wind, charged particles slamming in at a high percentage of the fraction of the speed of light, both electrons and protons and neutrons and alpha particles slamming in from the solar wind. And again, our atmosphere and magnetosphere protects us from all of these on Earth. But Ryugu was getting bombarded with this radiation for its entire history, 5 billion years. And so they figured, well, if we can get into the interior, we can find some more pristine materials. So JAXA had a very clever plan. They had a 2.5 kilogram copper sphere. This is about a 6-pound ball of copper, and it had to be fairly good size. And they had an independent, they didn't call it a gun, but a cannon. They had an independent cannon which they detached from the spacecraft, and it's falling very slowly toward the surface. While it's falling toward the surface, the spacecraft they have this device here, and then the spacecraft maneuvers around the other side of the asteroid. Why? Because this cannon is going to fire this copper projectile from about 500 meters away, and they're going to fire this 2.5 kilo copper cannonball with a 4.5 kilogram plastic explosive shaped charge. That's a lot of bang, friends. That's a lot of bang. I looked around. I did not find a projected impact velocity. It had to be going a couple thousand meters a second. Just huge. And they fired this off from 500 meters. So 2.5 kilogram copper projectile. I didn't do the math on this, but I'm imagining it's something on the order of 10 centimeters in diameter, 12 centimeters in diameter, something on that order, because it's solid copper. It's pretty beefy. This thing blasted a 10-meter wide crater on the surface of Ryugu. So this is our first asteroid impact test from the Japanese and their Hayabusa spacecraft. once they had this 10-meter wide crater, Hayabusa flies orbits back around to the other side, and they maneuvered, and the proboscis this time touches down inside the crater, and they went ahead and collected more material in their sample horn. And I said 2024 earlier. I was thinking of another mission. This mission brought its materials back to Earth in 2020, and they designed their flyby of Earth. Of course, the entire Hayabusa spacecraft did not re-enter. They jettisoned a heat-shielded cargo container in 2020, and it successfully landed in the Woomera test range in Australia. So this was Hayabusa, and they have about 35 kilograms of xenon propellant left. So Hayabusa is flying off in search of other targets in the solar system, which is exciting. Now, DART is different. DART wasn't interested in just disturbing the surface of an asteroid to collect some material. DART was there to test the simple idea: can we change the orbit of a satellite by striking it with a high velocity projectile? Some of you may have seen the 1998 film Armageddon, and I think that was Mel Gibson.
Film. I can't help it.
It was a good action film.
I'm not talking about science. I'm talking about as a film.
As a film, as an action film, very exciting. The science was a little bit shaky. I liked the Deep Impact film with Elijah Wood, which came out a few years later.
Bruce Willis
before he did Lord of the Rings.
Bruce Willis was Armageddon.
Bruce Willis was Armageddon. Okay, it was not Mel Gibson. Okay, there we go. No, Bruce. I should know this. Bruce Willis. Anyway, Elijah Wood. Elijah Wood's. Yes, and I loved when in Armageddon, I think it was Armageddon, the guy names the impacting object after his ex-wife.
Yes, which we can't say why he named her that, but okay.
No, he named it after his ex-wife. I'm like, oh, no, we cannot say. It's a family-oriented program. But let's just say he didn't like her much. Anyway,
get the book.
Yeah, go ahead and look at the movie. It's quite good.
It's funny.
So DART is different. DART decided, DART was there to say, can we actually do because that movie Armageddon, their plan was, we're going to split this in half when it's just beyond the orbit of the moon, and it'll fly past. The halves will split up, and it will fly past the Earth in two different directions.
So bad. That was that piece of it was so bad. You've got 10 seconds to explode it, or it's going to hit the Earth. No, that's not the way that works.
No, that's not the way that works. And in fact, we know an awful lot more about asteroids now than we did in 98. We know a great deal more. We knew virtually nothing about the surface of asteroids in 98. We didn't know a lot we knew about meteorites, but asteroids? We knew nothing. But the DART idea is, can we in fact do what they did in Armageddon in a realistic way? Change the orbit of an asteroid so it's deflected and flies past the Earth without striking, and saves lives, property, damage to the environment, the whole banana. And we think about this and we say, well, how bad could it be? Everybody knows about the dinosaur killer. The 10-kilometer wide, big as a mountain range, big as Mauna Kea, right? Big as Mount Everest. The dinosaur killer struck the Earth 65 million years ago and wiped out 75% of the species alive at the time. Yeah, that was a bad day. But we don't think those things happen very often. And it's really a rare. Hundreds of millions of years go by between events like this. On the other hand, the Chelyabinsk meteor. If you go to YouTube, friends, and you type in Chelyabinsk meteor or just Russian meteor, you should get, there was a lot of video of this. It struck the Earth in February of 2013. It was a very low angle impact, and it wasn't that big. We estimate the original object 20 to 30 meters. So as big as something between the size of a 2-story house and maybe like a commercial store you might see in your town, a small apartment building. And so this thing struck, and it burned through the top of the atmosphere. It's very low angle. So it spread its impact energy over a long path. And that was really good for us because this 20 to 30 meter wide object, it would fit quite tightly on a football field anywhere in the world. This thing released 400 to 500 kilotons of energy. The Hiroshima bomb was 15 kT. 15. And so if I take my handy calculator and I'm going to take the low number, I'm going to say, 400 kilotons divided by 15. And oh my God, that was 27 Hiroshima bombs on the low end. Yeah, bad day. The good news is most of the Chelyabinsk meteor blew up about 25, 30 kilometers up in the atmosphere. So it released its energy very, very high. It was on a very low angle path, so it spread that energy along a large 100 or 150 kilometer long pathway through the sky. So in spite of that, it blew out, it damaged about 1,500 buildings. It mostly blew out windows. Scores of people were injured by flying glass, shockwave, hearing damage, all sorts of crazy things. These asteroids in the 25 to 500 meter diameter are often referred to as city killers. I recommend you take a look at the book The Starry Room by Fred Schaff. Fred has a lovely scale for asteroids, which I taught for years. And city killer was one of the categories. Why do we call them that? Well, they're capable of destroying a modern urban metropolis. I'm not talking about a relatively small city like where I live, or Springdale, where Explore Scientific is located. I'm talking about wiping out the entire Fayetteville, Bentonville metropolitan area, the entire Memphis metropolitan area, the entire Chicago. Los Angeles metropolitan area.
I'm not wishing for Chicago, but
I when the Chelyabinsk meteor happened, and my students said, "Wow, what do you think about that?" And I said, I would give an awful lot to be present during a meteor impact event like Chelyabinsk. And they said, what would you do? And I said, well, you realize there's a substantial amount of time between the meteor flashing through the sky and the shock wave hitting. I said I would probably take some duct tape and tape my cell phone to my patio wall outside, and I would put on some protective goggles, and I would sit down in a chair with my tie on, and I would be prepared for my tie to be blown away like that famous audio commercial. And I said I would just sit there and wait to experience the impact. I would love it. And they said, well, what if you got hit by bits, pieces? I'd every year on St. Crispin's Day, I would strip my sleeves and show my scars, and said, these I had with Harry the King, as Shakespeare says in Henry V. Yes, I would proudly show those scars. I would love that. But yes, city killers.
But if you're too close, ducking isn't going to help.
It isn't going to help you. No. And they said, well, can you hear it coming? And I said, if you can hear it coming, it's time to put your head between your knees and kiss your bottom goodbye.
Yeah.
If you can hear it coming, it's going to be a really bad day. And this, you could see it. If you look at these videos, and there's a lot of dash cams and security camera stuff, and you see this streak go across the sky. And people go to their windows to look out. Wow, what's that? Look at this long, exciting cloud. And then, blam, the shockwave hits and blows the glass window in on them, which is not so good. But I would love to see a major meteor event like that. I would love to. These things, though, Paul, they're really hard to find. If you're talking anywhere from 25 to 500 meters, when you're talking about, we need to find these things when they're out by the orbit of Mars to take care of them, seeing something half a kilometer wide that's hundreds of millions of kilometers away, and these things are darker than coal. They're less reflective than fresh asphalt. If you think of fresh asphalt painted flat black, that's about what you've got. They are incredibly dark. Their albedos are down below 10%, which means they absorb 90 to 95% of the light that strikes them. They reflect almost nothing. And so detecting them is really, really hard. Infrared telescopes are much more capable of detecting them than optical telescopes are. So, and we don't have a really good, for infrared to work well, it has to be above the atmosphere. We don't really have a set of spaceborne or lunar placed infrared telescopes, which are wide angle, which will scan the skies looking for these monsters. We know where most of the big stuff is. And I see people all the time, we know where 90% of the asteroids are.
Yeah.
That just sounds like hubris to me. Just flat out going to put it out there. When somebody says, we know what all the threats are, I'm like, no, nature's going to get you. If somebody hears you saying that, no, it's going to be a bad day. So what happens when one of these city killers strike? It turns out we have pretty good accounts of one of the more recent ones, and this is the tale of a city called Tel El Hammam, which is in Jordan. It's near the mouth of the Jordan River. I'm not sure if it's in Syria or not. It's out toward the Dead Sea. Anyway, Tel El Hammam is the modern name for it, and it means the hill of El Hammam. El Hammam was a Bronze Age city, and this thing was 10 times larger than Jerusalem at the time. It was 30 or 40 times bigger than Jericho. It was the big trade route metropolis of its time. They got struck by a 200-meter impactor, something the size of a football stadium. Okay? Something the size of a football stadium. It's not that unimaginably big. 200 meters, a lot of department stores are bigger than that. It's not a particularly big rock as mountains or even hills go. A lot of hills are 200 meters. It's just not that big. But this thing came in nearly vertically, and it struck the ground. It struck the Earth at about 50,000 kilometers an hour. And these kind of objects don't survive through to the atmosphere generally. This thing probably airburst when it was about 10 kilometers off the ground, but that mattered not a whit, because what happens now is a superheated ball of vaporized stone and atmospheric gases comes slamming down, and it hits the ground at it's still moving about 10,000 kilometers an hour. And the resulting explosion was in the range of 20 to 50 megatons. It's just an insane amount of energy released. The Russians back in the day Stalin decided he wanted a 100 megaton bomb. And the scientists built it at 52 megatons, and they lied to him and said, no, it's 100, because they were afraid to build it bigger. They were just afraid to build it bigger. They said, oh, no. Yeah, the island they detonated it over pretty much is gone now. It's just a ridiculous explosion. For Tel Al Hammam, things like pottery melted into glass. They used adobe-style mud bricks. They boiled. The remaining moisture in them caused the bricks to liquefy and boil they made lava. Metal implements made of bronze, copper, and tin melted on the ground. Things like spears, bowls, swords, all these things just kind of melted into puddles. The surface temperature is estimated to have been something approaching 2,000 degrees centigrade, 3,600 Fahrenheit for our American friends. And if you imagine, this thing would have come in straight down, and as it hit, the shock wave would have spread out horizontally in all directions. If you've ever taken a water balloon and thrown it up and had it land on the pavement, you see this lovely radial splash pattern. Or if you've looked at rays in craters on the moon, much the same thing. And so this shock wave spread out over the ground. The city of Jericho was over 40 kilometers away, and the stone walls of the city were just knocked down in the blast. The shock wave disrupted the Red Sea, and you can imagine what happens when you put that much thermal energy on the ground. The atmosphere is heated and rises in a mushroom cloud, and it drew up from the ground sand and dust and a lot of water from the Red Sea. A lot of water from the Red Sea. And this sucked up all this salty water and rained down all this heavily salinated water. And it was even worse than that, because a lot of the water flashed off. And so it's basically raining salt over the entire area. There was no agriculture in the region of this city within, 75 to 100 kilometers of ground zero. No agriculture at all for 600 years. We call this city Sodom today. And we look at biblical accounts of a pillar of fire in the sky. Yeah, it must have pretty much looked like that. Here's a vertical asteroid strike coming down pretty much straight down, blam, and it hits. It would have looked like a pillar of fire. And then there would have been the mushroom cloud and the whole tale of don't look back. Well, if you were within 50 kilometers of that, you probably died. The shock wave, the heat pulse, if you were alive and in a building inside the walls of Jericho on the far side, yeah, I'm sure people survived. But if you've seen these films of atomic tests, where the first thing you see is the flash, and then trees and buildings and things catch on fire from the heat pulse, and then there's the huge shock wave. So you can imagine 25, 30, 40 kilometers away, people, animals, plants, building, anything flammable would have just burst into flame from the heat pulse, and then the shock wave would have knocked you down. In the city of Tel Al Hammam, where they've excavated it, they were looking, first they thought, the city was burned down. Maybe somebody came and just threw incendiaries. But they realized they had no technology that would reach 2,000 degrees centigrade at that time. They had no technology that would reach those temperatures. And then they looked for people, and all they found was minuscule bone fragments, which were all mixed up, like somebody had put them in a food processor and gone brrr, and put it on high. It was not a good day. So this is the kind of disaster. If this were to strike a major urbanized area today, millions dead, property damage that would literally throw our economy askew, and ecological effects that would last for decades. So, yeah, bad day. And for those of you interested, How Do You Know, episode 36, available on YouTube. You can search for that. That's our whole program on Tel El Hammam. So when we're saying, gee, what's the risk? What's the risk? Can I, should we prepare for something like this? Well, yes, we should. It's one of those things in physics and engineering lab we call a LFHC, low frequency, high consequence. Right? You think about bridge collapses. Does it happen very often? No. Consequences are really huge, so you have to take steps to ameliorate that risk. Same thing here. So could something like DART save us? Or certainly, if we see one of these things coming, we need a hero. And it's not going to be Bruce Willis. We need a hero.
You never know.
You never know.
You might sign up for it.
Yeah, possibly. But the nice thing is DART was an unmanned vehicle, and it was guided by the ground control folks until it got relatively close. Then it had cameras and software, and it was very much like DART was very much the civilian application of these guided cruise missile type things that we've seen used in combat situations around the world. They're commonly being employed in Russia against Ukraine. We're seeing these kind of guided missile technology. So much the same. The reason you can't fly it in like you can fly a drone into a target, of course, is that we need to hit these things when they're tens, maybe hundreds of millions of kilometers away. And the time lag means that you can't fly it by remote control. You have to, at some point, turn the control over to the machine and say, now, there's the target, fly yourself in. There's some good news here. Early detection is going to be, if we're going to save ourselves, early detection is key. So, yeah, spending money. Could we use Webb, which is an infrared telescope, to look for these threats? Yes, perhaps, and maybe we will. It's not really designed for that because Webb tends to be a narrow field, highly magnified, tightly focused instrument. But something like Webb that was wide field and designed to look for these threats would be very useful. The nice thing is that orbital tracking and prediction is accurate enough today that we can predict the threat hazard level years in advance. And that's going to be crucial. We talk about asteroids like Apophis, which is supposed to fly by the Earth and be very close in the 2030s. And we talk about these and we go, okay, could we deflect these things? Now, you got to have your math right, because the horror scenario is, well, it was going to miss, but we bumped it the wrong way. And now the guided missile is flying towards us again. That would be really bad. But the good news is that it's our math and our technology and our understanding of gravitation and how these things fly through the solar system is really indeed very accurate. And we need to target these things far away. And I think I can share a screen with everybody. There we go. Screen sharing. Screen 2, share. Bingo, there we are. Now, the first scenario, A here, this is like the movie Armageddon. Let's wait till it gets really close and we'll hit it with a really big nuclear weapon. And in fact, what Bruce Willis does in Armageddon, we're going to drill into it and put the nuke inside it, would be kind of like almost as bad a thing as you could possibly do. But the DART scenario, there is scenario B. That's where we have early detection and early deflection. The nice thing is, from 100 million kilometers away, we only need a very tiny 0.007 degree deflection. That's not very much. All we've got to do is miss by a little. And so we go ahead and we have our impactor here, and we see that, oh, if we're going to get a big deflection angle, we need a big impact. Whereas a small deflection doesn't require as much of an impact. And it turns out that's a really good thing, because a lot of the asteroids we see today are what we call rubble piles. And we'll talk a little bit more about that as we move further on in the program. But when we look at these deflections and these impacts, we want to get it as far away as we can, because a very small deflection here can cause a miss. And as the proverb says, a miss is as good as a mile. And the interesting thing, because kinetic energy goes by the square of velocity. So if we need a angular deflection that is 10 times bigger, it takes 100 times more impact energy. Again, these are back of the envelope calculations here, friends. I am not that kind of orbital mechanics scientist to calculate these things to a nicety the way some of the space agencies do. But I do know that a larger change requires a lot more kinetic energy, and that's a big issue. So let's see, picture. No, I don't want picture in picture. I don't want to cast it. Oh, we've done this before. Web select? No. Web capture? Oh, bugger.
It should just say stop sharing in the original window.
Yes, let's try that. Toggle screen sharing. That's what I needed to do. And toggle camera preview. And let's get rid of the picture in picture. Hey, we're back. Isn't technology a joy? Anyway, so how well did DART do? That's a question people say is, oh, well, did it work? And one of the frustrating things is you get this big buildup in the media. DART's coming, DART's coming, DART's coming. And I don't know if you saw these things, Paul, but I'm sure a lot of our viewers who are space science oriented have these feeds on their computers and their phones, and you saw these things. DART's coming, and it was very exciting. And then, oh, it hit. And then we were saying, well, did it work? And NASA said, give us a few weeks to figure it out. One of the problems is with the asteroid, which was Dimorphos, being so far away and small and dark, it's hard to see. You need Hubble class or Keck class or Webb class telescopes to see what's going on. The other problem is that when it struck, it made a titanic debris cloud. The debris cloud stretched for over 100,000 kilometers at one point. So seeing what's happening through this cloud of brightly reflective debris made things harder. What the scientists at NASA were hoping for was to change the orbit of Didymos by 73 seconds or more. Anything over 73 seconds would have been a measurable change to the orbit. It would have been a success. Yay, we win. We actually changed the orbit by 32 minutes. Think about that. We changed the orbit by 32 minutes. We did 25 times bigger change than we were hoping for as a minimum. And this is kind of the hallmark of NASA. Oh, we're going to go up for a 90-day mission, and 15 years later, the rover is still running. This is kind of their hallmark. Under promise, over deliver, which, I think a lot more government agencies could adopt that philosophy.
Heresy.
Under promise, over deliver.
Heresy, I'm telling you.
The interesting thing is we now think that we can redirect a city-sized asteroid. Let's see if we can show you this lovely diagram. Here's what we did, and tell you a little bit about why we chose Dimorphos. Dimorphos is a moonlet of the asteroid Didymus. Now, Didymus is quite formidable. Didymus is around 840 I have kilometer there. That's an error. It's an 840 meter wide asteroid. It's in the 1 kilometer class. An asteroid like Didymus hitting the Earth would be catastrophic. Huge numbers of species, including almost certainly us, going extinct. Something like Didymus hitting us would be a really bad day. Dimorphos is about 20% of the size. It's about 170 meters wide. 170 meters wide is about the size of the asteroid that clobbered Tel al-Hammam. So we're talking an asteroid that could destroy an urban area and kill millions. And if it hit in the ocean, that would hardly be any better. We would have massive tsunamis that would circle around the world several times before they settled down. That might even be worse. But in any case, you can see where the green path, the little DART spacecraft, which was basically about the size of a refrigerator, and it was flying in at over 10,000 kilometers an hour, and it struck Dimorphos anti-orbital. So it basically struck Dimorphos head on. The idea was, can we slow it down? The reason we chose, why didn't we move it to the side or hit it from behind? We wanted no chance whatsoever that Dimorphos would be blasted out of its orbit around Didymus. The nice thing about this system with Didymus and Dimorphos, Dimorphos was already captured. And if we slow its orbit down and make it go closer to Didymus, there's absolutely zero chance that we could, whoopsie, accidentally slam it and have it go off into an independent solar attitude. And this thing is already Earth grazing. It comes out towards Earth's orbit every once in a while. We did not want to fiddle with this and make it a hazard. This is why we picked Dimorphos, because it's a bound moonlet. And so shrinking its orbit meant that we were absolutely not going to have, and let's see, what do I need to do here again? I just did it. Stop sharing here. Toggle screen sharing.
I got a question.
Yes, sir.
So,
sure.
You change the orbit of the moon. They're
correct.
Obviously locked into each other.
Yes, they are.
So I'm thinking that you have the proverbial bicycle wheel, right? And
okay.
You spin it, right?
Right.
And it's really hard to just have it in your hands, not attached to a bicycle. It's really hard to move around when it's spinning.
Correct.
So that makes me wonder if we've tightened the orbit of the smaller body, could that cause the larger one to change its orbit over time? Because now it's different.
Unlikely. If you think about two objects, and I'm going to make a science experiment here. real quick on air. So I've got a clay ball here, and I'm sticking it onto the end of a ballpoint pen. And I've got this other bigger clay ball, and I'm sticking it. And we know this is going to balance
Raise it up
somewhere. There we go.
We can't see it.
And I balance this. I don't know if you can see this. Here we go. I've stuck this clay ball, and I'm balancing this on my finger. There we go. This balance point right here for Dimorphos and Didymus, this is called the barycenter. And it's actually the barycenter that orbits the sun. And it turns out if we spin this, both Didymus and Dimorphos spin around. This barycenter point is out in space, and it makes this truly a binary asteroid because they orbit around a common point. This is like Pluto and Charon in our own solar system as a binary planet. Well, when we have this, by shifting this in farther, we change the barycenter, but only very slightly because we're changing the small one. Remember, this is only 20% of the size. This is really much too big. And so when we talk about our asteroid pair, we can't, by fiddling with this and making it go closer, we can't really change the barycenter very much. If we were to have a much bigger spacecraft and whack the big one, we could indeed change it so that maybe this one, through orbital instability, would then fly off. Dimorphos could fly off, and then it would be, I don't know, that it would be very hard to predict where it was going, and that might be very bad. So we chose to change the orbit of the small one, which isn't going to affect the barycenter much. So the orbit of this pair around the sun isn't really going to be deflected very much. We'll have to look over the next couple of years and see if we can even measure any deflection of the orbit of the two of them. But really, since this little boy was captured in the gravity well of the bigger Didymus captures Dimorphos, by slowing it down, we're not going, there's virtually zero chance that this is going to come flying off and become an independent object orbiting the sun and maybe hit somebody. There's virtually no chance of that.
Well, I was thinking that the pair's orbit around the sun would be changed.
Well, that's just it. Most the barycenter, the balance point between them, is what actually orbits the sun.
Yeah.
And by striking the little one, because it's so much smaller and so much less massive, there's really no chance that we're going to disturb the barycenter very much, and that's the only way we can change the path around the sun.
So you're saying it changes it a touch, but it may be 1 billion years before we notice anything.
Yeah,
it's so small.
Yes, and we have the orbit of the pair predicted to a nicety, and it will be interesting to see because it's an Earth-grazing asteroid, so it has an orbit about a year long. It will be interesting to see in the coming years if it deviates from its predicted path from this event, but I would think this would be in the matter of very, very tiny deviations, minutes or perhaps seconds per year in its orbit. Nothing that's going to be a major change or any kind of a threat.
Okay.
So, go ahead.
I said okay. I was just curious.
So that's why we picked this binary asteroid to test. Dimorphos, the little one we hit, is estimated to have a mass of about 5 billion kilos. That's not very big. That's the mass of a modern skyscraper. It's about the same as the Pyramid of Giza, the Great Pyramid of Giza, if that helps you. And it's an extremely low density object. It has a density of only about 2.2 grams per centimeter square. this is for a rocky object. This is a really low density. A rock on Earth is about 5.5 grams per cubic centimeter. Lunar rock, which contains lighter minerals, about 3.5 to 4 grams per cubic centimeter. This 2.2 gram per cubic centimeter means that Dimorphos is probably a rubble pile, which means you've got a lot of rocks and dust and boulders which have simply accumulated due to mutual gravity. There is some thought that rubble pile asteroids were originally a solid piece. Something gave them a big whack and blasted them into fragments, but the fragments fly away, and then through mutual gravitation, they reassemble themselves. It's like some kind of Marvel movie supervillain. Well, we hit, missed the reassembler with a grenade, and blam, there's meaty pieces all over, but they slurp back together and reassemble themselves. It's like some creepy horror movie. These rubble piles, we think when they get smashed, it may take them anywhere from a few hours to maybe as much as several weeks to reassemble. You think about the Bruce Willis solution on Armageddon, what's sometimes called the big bomb solution. If we went and drilled inside and planted a nuke and then set the timer and flew away, this thing flying towards the Earth is going to explode, and then without changing its path, because the center of gravity hasn't been changed, it's just going to reassemble itself. And it would be like, we killed it, yay, oh damn, it's reassembling itself, we're in as much danger as before. It would be kind of a really sad outcome. These rubble pile asteroids have really been a surprise. The most recent one is the OSIRIS-REx asteroid explorer that targeted asteroid Bennu. And that was in the news. And OSIRIS-REx had this idea, we're going to had a proboscis type of thing with a little sample collector on the bottom. We're going to touch down, and we're just going to touch down and bump it and see if we can bump a little material into the cup. And then we're going to blast some nitrogen gas. So we kind of agitate the stuff, and hopefully some of it falls back into our cup. And they were hoping for a few tenths of a gram up to maybe a few grams. And what happened when they touched down on the asteroid Bennu, the proboscis sank in half a meter. So think of this, you're flying down towards what looks like a solid surface, and you're coming down at a fraction of a meter per second. You're just literally very slowly drifting down, and you hit the surface and you just start sinking in like it's mud. And they sank down half a meter, and they hit the nitrogen jets. They think they excavated about 6 metric tons of rock. They were hoping for a maximum of a few grams. They got so much stuff, they had problems getting the sample container shut. And they had to actually shake and vibrate the spacecraft so they could get rid of the extra and get this sample container shut. And this is the one that should be back to us in 2024. And like the Hayabusa spacecraft, OSIRIS-REx will make a flyby past the Earth. It will fly within about 100, 120 kilometers, which means it will be up in the general region of where satellites and space stations are. So everybody watch out. And then they're going to jettison their sample container and a little heat shield reentry vehicle, and it's going to come down in the desert in Utah, and it will be landing there. And we hope to recover, they think they've got several kilos of material from asteroid Bennu, which is really, really exciting. And so we continue to explore asteroids, and we're finding out that they're nothing like we thought. Science fiction has written for decades. Oh, an asteroid miner ship, and the asteroid miners fly, and they get explosives and drills, and they drill into the asteroids looking for things. You know what? A lot of the asteroids are not solid. And if you hit them with a nuke, the rubble pile ones, if it was a big enough nuke, it would just fly off and become a cloud of debris. So it may be entirely possible to kill an asteroid the size of Didymos, which would be maybe in the kilometer class. If this thing isn't solid, if it's a rubble pile style asteroid, we could kill it. Whether we want to do that or we want to deflect it, of course, if it's solid, if it's a metallic asteroid, what's the one they're talking about? Psyche, I think, then that might be a different story. But we know we can nudge them off course. And all we have to do, if we're 100, 200 million miles away, all we have to do is nudge them a little bit and they go flying past instead of striking head on, which is what DART is all about. I hope, yes, thank you, Paul, putting up the banner there for Star Mentor. If you haven't got a copy, I hope you'll pick one up. More than 50 activities for you with your small telescope and binocular. For those of you asking, what do I do next? Where do I go? How do I navigate around the sky? What am I looking at? How do I find different types of object? Star Mentor is your guide. And do we have any questions? I know we're just about out of time. Do we have any questions in the chat or anything that was interesting today?
Mike Overrecker was telling us about all the different asteroids that he's collected.
Oh, meteorites. Yes, meteorites are wonderful.
And he commented right before you spoke about the people completely ignoring the Chelyabinsk, whatever it is.
Oh, Chelyabinsk?
Yeah. You addressed what he was saying, so I didn't interrupt. Senthil says hi, and Ronnie Guest says it's very interesting. He's appreciate it. And Osmosis 007 says howdy.
Our old friend. Well, good. Good. I'm glad everybody enjoyed it. And next week, I believe we're going to skip a week because I'm out all weekend at the Dark Sky Festival, so I will not have my weekend to prepare. So I'm looking at my calendar, and our next Monday will be October 31st. And maybe I should have saved the asteroid impact scary story for Halloween, but we'll do something fun for Halloween and for next weekend. As I say, if you're anywhere within range of Northwest Arkansas, I encourage you to look up the Arkansas Dark Sky Festival and come and see me. I'll be appearing there, and I hope you'll join me, and I hope you'll pick up a copy of Star Mentor, and we'll see you again in about 2 weeks. Thanks, everybody. Bye-bye.